They told the public it was just another winter anomaly, an unfortunate alignment of cold air, unlucky timing, and nature doing what nature has always done. Headlines called it extreme, rare, unexpected. Meteorologists labeled it a freak event. And most people accepted that explanation because it was familiar, comfortable, and simple. But sometimes the simplest explanations are the ones that hide the most important details. Because just days before this historic freeze locked cities, shattered infrastructure, and turned highways into frozen corridors of abandoned vehicles, something else happened far above the clouds, far beyond the reach of daily forecasts. Something most people never heard about, and those who did were never told why it might matter. 3 days before the cold arrived, the sun unleashed a powerful surge of energy directly toward Earth. Not a metaphorical surge, not poetic language, a real, measured, documented burst of radiation and charged particles that slammed into our planet's magnetic defenses with extraordinary force. It wasn't subtle. It wasn't minor. It was the kind of event that space weather scientists track minute by minute, the kind that triggers alerts, emergency briefings, and quiet concern inside research centers that rarely make headlines. And yet, while this cosmic impact unfolded in silence, the public was being told to prepare for snow, not to question the sky itself. The timing alone is unsettling. When one rare event follows another with near-perfect precision, scientists usually pause. They compare data. They examine correlations. They ask uncomfortable questions. But in this case, those questions never made it into mainstream conversation. Instead, the story was neatly divided into 2 separate worlds. One story belonged to meteorology, grounded in clouds, temperatures, and jet streams. The other belonged to astrophysics, locked away in discussions about solar flares and magnetospheres. The assumption was simple. What happens in space stays in space. What happens in the atmosphere happens below. End of discussion. But nature does not recognize the boundaries humans draw between scientific disciplines. The Earth is not layered like a textbook diagram with sealed compartments that never interact. It is a dynamic, interconnected system, constantly exchanging energy between surface, sky, and space. And when something powerful strikes that system at exactly the wrong moment, the effects may not remain isolated where we expect them to stay. In the days leading up to the freeze, Earth's magnetic shield absorbed an unusually strong hit. This invisible barrier, which quietly protects life from solar radiation every second of every day, was forced to flex under pressure. Instruments detected disturbances rippling through near-Earth space. Satellites registered anomalies. High-latitude skies erupted in light displays far outside their normal range. These were not random glitches. They were signals. Signals that something out of the ordinary was unfolding above our planet. At the same time, deep within the atmosphere, something else was beginning to destabilize. A massive reservoir of Arctic air, normally confined near the pole by powerful winds, was losing balance. Subtle shifts appeared in atmospheric models, the kind that forecasters often overlook until they suddenly matter a great deal. The system was already strained, already vulnerable, and then, almost as if on cue, it broke. When the cold finally arrived, it arrived with violence. Temperatures collapsed at a speed that shocked even experienced forecasters. Power grids failed under demand they were never designed to handle. Entire regions became unlivable overnight, and as millions of people struggled to stay warm, the official explanation settled into place with comforting certainty. A rare winter storm, nothing more. But explanations gain credibility not just from repetition, but from completeness. And this one leaves too much out. It asks us to ignore what happened just days earlier. It asks us to believe that a major disturbance in Earth's magnetic environment occurred at precisely the same moment as one of the most extreme winter outbreaks in modern history. and that the two events share nothing beyond coincidence. That may be true. Coincidences do happen, but when they happen this cleanly, this precisely, science usually demands a closer look. What makes this story different is not speculation, but silence. The data exists. The timestamps are public. The measurements are real. Yet the conversation never expanded beyond the lower atmosphere. No one asked whether energy injected from space could matter when atmospheric systems are already on edge. No one explored whether Earth's weakening magnetic field might be changing how such events unfold. And no one explained why skies lit up in places that had no business seeing auroras just days before the cold descended. This is not about fear. It's not about rewriting weather science. It's about acknowledging that the planet we live on is more exposed, more interconnected, and more sensitive than we often assume. The sun is not just a distant light source. It is an active, unpredictable engine capable of reaching deep into Earth's environment when conditions allow. And sometimes, those conditions line up in ways that challenge our assumptions. As we move forward, we will slow down the timeline, examine the physics, and separate what is proven from what is possible. We will look at what scientists agree on, where they disagree, and why certain questions remain unanswered. Not to claim certainty, but to understand why certainty may be premature. Because once you notice how precisely these events align, it becomes very difficult to look at that winter storm as just weather. And if that connection exists, even faintly, it changes how we understand risk, prediction, and the forces shaping our future. The cold was only the surface story. What happened above it may be the part we can no longer afford to ignore. The moment electrical currents intensify, the atmosphere becomes restless in layers most people never think about, yet those layers are not isolated. They are connected by waves, chemistry, and electricity in ways scientists are still working to fully understand. At the same time, the lower atmosphere was already under strain. Long before the cold arrived, the Arctic region was experiencing unusual pressure patterns. Winds that normally confine freezing air near the pole were weakening. This didn't guarantee a disaster, but it created vulnerability. Think of it like a fault line under tension. Most of the time, nothing happens, but introduce a sudden disturbance at the wrong moment, and the system can shift abruptly. This is where timing becomes everything. The solar storm did not arrive weeks earlier or weeks later. It arrived during a narrow window when the atmosphere was already unstable. Models that usually offer forecasters a comfortable margin of warning struggled to keep up. Signals that typically develop slowly appeared rapidly, almost as if the atmosphere had crossed a threshold. Within hours, projections shifted. Within days, the outcome became unavoidable. Mainstream explanations focus on known atmospheric processes, and they are not wrong. Sudden disruptions of Arctic air have happened before. Cold outbreaks are not new. But what is rarely discussed is whether external energy sources can influence when those disruptions occur, especially when the system is already near a tipping point. Science often treats the atmosphere as if it exists in isolation, but that assumption is one of convenience, not necessity. Earth is constantly exchanging energy with space. Charged particles flow along magnetic field lines. Electrical currents connect the upper atmosphere to the surface through a global circuit that never shuts off. Gravity waves ripple upward and downward through atmospheric layers like vibrations through a stretched membrane. None of these processes operate independently. They overlap, interact, and sometimes amplify one another. During the days surrounding the solar impact, instruments recorded unusual behavior across multiple regions of near-Earth space. Satellites experienced drag changes caused by atmospheric expansion. Radio signals fluctuated. Power systems registered induced currents far from polar regions. These are not speculative claims. They are documented effects of geomagnetic disturbances. What remains uncertain is how far down the influence can travel when conditions align just right. One of the most overlooked signals came from the sky itself. People across parts of the southern United States reported seeing strange glows, colors that didn't belong there. Auroras, usually confined to polar regions, crept far south, quietly announcing that Earth's magnetic shield had been pushed beyond its usual limits. To most observers, it was a beautiful curiosity. To scientists, it was a warning sign that charged particles were penetrating deeper than normal. These visual phenomena matter because they are evidence, not theory. They show that energy from the sun reached places it normally doesn't. And if that energy reached deeper into the atmosphere than usual, the question becomes unavoidable. What else did it touch along the way? None of this means the solar storm caused the freeze in a simple, direct way. Nature rarely works like that. Instead, the more plausible question is whether it acted as a trigger, an amplifier, or a destabilizing influence on a system already under stress. Complex systems don't always need large pushes. Sometimes they only need the right push at the wrong time. This is where scientific discomfort begins, because proving such an influence is extremely difficult. You can't rerun Earth's atmosphere like a laboratory experiment. You can't rewind the sun and change one variable at a time. What scientists rely on instead are patterns, correlations, and physical plausibility. And in this case, the pattern is difficult to ignore, even if it remains unproven. What makes this especially important is that Earth's protective magnetic field is not as strong as it once was. Measurements show a gradual weakening over decades, with certain regions thinning faster than others. A weaker field means less shielding. Less shielding means solar energy penetrates deeper. And deeper penetration means interactions we may not yet fully account for in our models. If that trend continues, events like this may not remain rare coincidences. They could become stress tests, revealing weaknesses in systems we assumed were independent. Weather forecasting, infrastructure planning, and risk assessment all depend on assumptions about stability. When those assumptions quietly shift, the consequences can be severe. The storm that followed did not care about explanations. It tore through power grids, froze water systems, and exposed how fragile modern life becomes when temperature drops faster than preparation can keep up. And while attention stayed focused on snow totals and wind chill, the deeper question remained unanswered. Did something from above help tip the balance? As we move forward, we're going to slow the story down even more. We'll walk through the exact sequence of events with timestamps, data, and physics. We'll look at what space weather scientists saw, what meteorologists saw, and where their timelines unexpectedly overlap. Because once you lay the two stories side by side, it becomes harder to pretend they belong to separate worlds. And that's where the investigation truly begins. When you align the timelines side by side, the separation between space and weather begins to feel artificial. On one track, satellites watched the sun erupt, ejecting a massive cloud of magnetized plasma hurtling toward Earth at millions of miles per hour. On another, atmospheric models quietly began to drift away from their usual behavior, showing early signs end of the severity scale. When one does, scientists pay attention, not because disaster is guaranteed, but because the system is being pushed closer to its limits. On this occasion, those limits were tested while Earth's atmosphere was already unsettled. Within hours of the solar impact, Earth's magnetic field showed clear signs of stress. Measurements revealed rapid fluctuations, strong currents, and energy transfer into regions that normally remain relatively calm. The upper atmosphere heated and expanded, increasing drag on satellites and altering the environment in which atmospheric waves travel. These are not abstract effects. They change how energy moves vertically through the atmosphere, even if the magnitude of that change is small. Small changes matter when systems are nonlinear. The atmosphere does not respond proportionally to every input. Sometimes it absorbs disturbances without visible effect. Other times, a minor nudge can reorganize circulation patterns on a massive scale. This is why forecasting remains probabilistic rather than deterministic. The system is sensitive, complex, and full of thresholds we don't fully understand. As the days passed, forecasters noticed something unsettling. The usual lead time for predicting a major cold outbreak was shrinking. Signals that normally strengthen gradually were accelerating. Model outputs began to diverge more than expected. The Arctic circulation, usually a reliable anchor, was behaving unpredictably. It wasn't that scientists were wrong. It was that something was changing faster than anticipated. Then the cold air broke free. When it did, it moved with remarkable speed. Temperatures collapsed across vast regions in a matter of hours. Infrastructure designed for gradual winter stress was suddenly overwhelmed. Power plants tripped offline. Water systems froze. Emergency declarations spread from state to state as officials scrambled to respond. The storm didn't just challenge comfort. It challenged assumptions about preparedness. Throughout this period, the solar event faded from public discussion. It had done its damage quietly, without spectacle beyond a few stunning night sky photos. Yet its fingerprints remained in the data, embedded in measurements few outside the scientific community ever examine. The public narrative moved on, satisfied with a familiar explanation, while an opportunity for deeper understanding slipped past. This is not an accusation. Science is cautious by design, and rightly so. Extraordinary claims demand extraordinary evidence. No responsible researcher would declare a causal link without rigorous proof. But caution becomes a problem when it turns into dismissal, when questions are avoided rather than explored because they sit uncomfortably between established frameworks. The real issue is not whether this single storm was influenced by space weather. The larger issue is whether our models are missing interactions that could become increasingly important in the future. Earth's magnetic field is weakening slowly but measurably. Solar activity follows cycles, some more intense than others. Human-driven climate change is loading the atmosphere with additional energy, altering circulation patterns, and pushing systems closer to instability. These trends do not exist in isolation. They overlap. If extreme weather systems are becoming more sensitive to disturbances, then influences that were once negligible may begin to matter, not as primary causes, but as triggers, as timing factors, as final straws that tip already strained systems into chaos. Ignoring that possibility does not make us safer. Investigating it might. As we continue, we'll take a closer look at the physics behind these interactions, what scientists know, what they debate, and where the evidence remains thin. We'll examine why some researchers believe the connection is implausible, and why others argue it deserves serious attention. Because understanding what happened is not about assigning blame to the sun or rewriting meteorology. It's about recognizing that the planet operates as a whole, not as isolated layers. And once you start viewing Earth that way, the storm no longer looks like an isolated event. It looks like a warning. Warnings are often misunderstood because they rarely arrive as clear messages. They arrive as patterns, anomalies, and events that don't quite fit the stories we tell ourselves about how the world works. This was one of those moments. Not dramatic in the way movies portray disasters, but quietly unsettling in how neatly everything lined up. A powerful solar disturbance, a stressed atmospheric system, a rapid collapse of stability. Each element on its own is explainable. Together, they form a question that refuses to go away. To understand why scientists hesitate here. you need to understand how weather knowledge is built. Modern forecasting relies on numerical models that simulate the atmosphere using equations describing fluid motion, heat transfer, and radiation. These models are incredibly sophisticated, yet they are still simplifications. They cannot include every variable, every interaction, or every feedback loop. Decisions are constantly made about what matters most and what can be safely ignored. Historically, influences from space were placed firmly in the safe-to-ignore category when it came to day-to-day weather. That decision wasn't careless. It was practical. For most of recorded history, the effects of space, weather on surface conditions, appeared negligible. Solar storms disrupted communication, navigation, and technology, but snow still fell because of pressure systems, not plasma clouds. Over time, this became an assumption so deeply embedded that it stopped being questioned. And once assumptions become invisible, they are rarely tested. But assumptions deserve re-examination when conditions change. Earth today is not the Earth of a century ago. The atmosphere, it does not respond only to the biggest input. It responds to timing. Think of it like a glass balanced at the edge of a table. A heavy push will knock it over, but so will a light tap if the glass is already unstable. The atmosphere, during that period, appears to have been very close to the edge. The solar disturbance may not have been the shove. It may have been the tap. This idea unsettles many scientists because it challenges a comforting belief in separability, the belief that we can neatly categorize causes and effects, the belief that we can say with confidence where one influence ends and another begins. Reality is rarely that tidy, especially when dealing with systems as vast and complex as Earth's atmosphere. There is also a psychological component at play. Extreme events demand explanations, and simple explanations are easier to communicate. Saying a rare winter storm occurred satisfies the immediate need to understand. Saying a rare winter storm may have been influenced by a chain of interactions involving solar activity, magnetic fields, atmospheric instability, and electrical coupling across multiple layers of the planet is far less comforting. It introduces uncertainty, and uncertainty makes people uneasy. But uncertainty is not the enemy of science. It is its fuel. The most important advances often begin with discomfort, with observations that don't quite fit existing models. Ignoring those observations doesn't preserve certainty. It only delays understanding. What makes this moment especially significant is that similar alignments have been appearing more frequently in the historical record. Severe solar storms followed closely by unusual atmospheric behavior. Polar disruptions occurring during periods of heightened geomagnetic activity. Auroras appearing far outside expected regions, just before major weather shifts. None of these alone prove anything. Together, they form a pattern worth investigating. This does not mean rewriting everything we know about weather. It means expanding the frame. It means acknowledging that Earth is part of a larger system, constantly interacting with its environment. The Sun is not a distant background actor. It is an active participant. And Earth's magnetic field is not an impenetrable shield. It is a dynamic structure, changing over time. As we continue deeper into this story, we'll examine the specific mechanisms scientists propose, the reasons many reject them, and the evidence that keeps the debate alive. We'll look at how energy moves through the atmosphere, why the polar circulation is so sensitive, and what happens when multiple stressors converge. Not to declare a verdict, but to understand why the question exists at all. Because once you see how interconnected these systems are, it becomes impossible to pretend that what happens above our planet is irrelevant to what happens on its surface. And that realization may be the most important takeaway of all. What comes next is where the story becomes less speculative and more structural. Because once you move past the surface events, and look at how Earth actually moves energy, the idea that space and weather are disconnected begins to collapse. Not dramatically, not all at once, but slowly, through details that are easy to miss unless you know where to look. High above the clouds, in a region most people never think about, lies a thin, electrically charged layer of the atmosphere known as the ionosphere. It is shaped by sunlight, energized by solar radiation, and tightly linked to Earth's magnetic field. Every day, this layer swells and contracts, responding to changes in solar activity. During calm periods, its behavior is predictable. During solar disturbances, it becomes volatile. And volatility in this region matters, because the ionosphere is not isolated. It is connected to the lower atmosphere through waves, currents, and momentum transfer that scientists are only beginning to fully map. When a strong solar event strikes Earth, the ionosphere heats rapidly. That heating causes expansion, pushing atmospheric mass upward and outward. This expansion doesn't stop at a single altitude. It alters pressure gradients and density profiles, changing how energy travels vertically. Atmospheric waves that normally dissipate harmlessly can reflect, amplify, or redirect. These waves don't carry temperature in the way we usually think about weather, but they carry momentum, and momentum shapes circulation. At the same time, geomagnetic storms intensify electrical currents flowing through the ionosphere. These currents are part of a global electrical system that extends from thunderstorms near the surface all the way into space. Under normal conditions, this circuit operates quietly in the background. During geomagnetic disturbances, it becomes more active. Voltages shift, currents strengthen, and while the effects at the surface are subtle does not mean irrelevant when systems are already stressed. Now consider the polar regions, where Earth's magnetic field lines funnel charged particles directly into the atmosphere. These regions are uniquely sensitive to space weather. Energy input there is far greater than at lower latitudes, especially during solar storms. This energy heats the upper atmosphere unevenly, creating pressure differences that can ripple downward. The polar atmosphere is not just cold, it is dynamically fragile. It relies on strong, stable circulation to keep Arctic air locked in place. That circulation, often described as a polar vortex, is not a single storm, but a vast ring of winds spanning thousands of miles. When it is strong, cold air stays confined. When it weakens, that air can spill southward in dramatic fashion. Traditionally, disruptions to this system are explained through atmospheric processes alone. But when external energy is injected into the polar upper atmosphere, it adds stress to an already delicate balance. During the period leading up to the freeze, measurements showed unusual heating in the upper polar atmosphere. This heating did not directly create cold at the surface. Instead, another overlooked factor during this period was atmospheric coupling, the process by which changes in one layer influence others. Coupling is often weak and easily ignored. During extreme events, it strengthens. Energy moves more efficiently across layers. Disturbances propagate farther. Feedback loops tighten. What happens high above the surface begins to matter more than usual. This matters for a simple reason. Forecasting models are optimized for average conditions. They are built on decades of data that assume certain boundaries remain stable. When those boundaries shift, even slightly, error margins grow. And when multiple shifts occur at once, predictability collapses faster than models can adapt. The freeze exposed that vulnerability, not because scientists failed, but because the system behaved in a way that our tools are not yet designed to fully capture. The storm was not unprecedented in isolation. What made it dangerous was the speed, the reach, and the lack of warning. And that brings us to the uncomfortable implication. If space-driven disturbances can act as timing accelerators rather than primary causes, then future extremes may arrive faster than expected, even if their general possibility is known. Preparedness depends not just on knowing what can happen, but on knowing when it might happen. As solar activity continues to fluctuate and Earth's magnetic shield continues to weaken, these interactions may grow more relevant, not less. Combined with a warming climate that pushes atmospheric systems closer to instability, the risk is not that every solar storm will cause extreme weather, but that some storms will arrive at exactly the wrong moment. This is why the question matters, not to assign blame to the sun, not to undermine established science, but to recognize that Earth does not operate in isolation. It is part of a constantly interacting system, where influences stack, overlap, and sometimes align in ways that challenge our expectations. And as we move further into this investigation, the focus will shift from what happened to what it means going forward. Because the real story is not about one freeze. It's about what happens when multiple fragile systems collide. What it means going forward is where the stakes quietly rise. Because once you accept that Earth's atmosphere can be influenced by forces beyond its lower layers, preparedness becomes a much more complex challenge. The question is no longer whether extreme weather will happen. That much is already clear. The question becomes how fast it can unfold, and how little warning we may have when multiple stressors converge. Historically, societies adapted to weather patterns that changed slowly. Seasons shifted, climates evolved, but the pace allowed infrastructure, agriculture, and forecasting to adjust. Today, that margin is shrinking. Modern systems are optimized for efficiency, not resilience. Power grids are tightly balanced. Supply chains rely on precise timing. Emergency response plans assume predictable lead times. When events accelerate beyond those assumptions, even well-designed systems begin to fail. The freeze demonstrated this with uncomfortable clarity. Regions unaccustomed to sustained cold found themselves facing conditions they had never planned for. Equipment failed not because it was poorly built, but because it was never designed to operate outside a narrow temperature range. Backup systems froze, redundancies vanished, and the failure cascaded, moving from energy to water to transportation in a matter of hours. From a scientific perspective, this cascade is just as important as the initial trigger. Extreme events rarely cause damage directly. They expose hidden fragilities. They reveal where assumptions about stability no longer hold. In this case, the assumption was that weather systems evolve slowly enough to allow reaction. That assumption may no longer be safe. Space weather complicates this picture because it operates on a different clock. Solar eruptions do not give weeks of warning. Once a major burst of energy leaves the sun, Earth has hours to days at most before impact. That energy can arrive while atmospheric systems are already under strain, compressing timelines even further. What might have been a gradual shift becomes an abrupt transition. This raises an uncomfortable possibility. Forecasting may need to evolve beyond the atmosphere alone. Integrating space weather data into long-range risk assessment could become necessary, not because solar storms dictate weather, but because they may influence its timing. Timing is everything when it comes to preparedness. Some researchers are already exploring this idea, quietly and cautiously. They are examining correlations between geomagnetic activity and atmospheric anomalies. They are studying how upper atmospheric heating affects wave propagation. They are modeling scenarios where small external disturbances coincide with internal instability. Progress is slow, not because the work lacks value, but because it challenges deeply rooted assumptions. There is resistance, and that resistance is understandable. Science advances by skepticism. Many experts argue that the energy involved in solar storms is trivial compared to the energy driving weather systems. In absolute terms, they are correct. The sun does not inject enough energy to directly power storms or cold outbreaks. But this argument misses the point. The issue is not magnitude, it is sensitivity. A system near equilibrium can absorb large disturbances without visible change. A system near a threshold can respond dramatically to a minor input. Climate change, Arctic warming, and shifting circulation patterns may be pushing the atmosphere closer to those thresholds more often. In that context, influences once considered negligible deserve reconsideration. This does not mean panic. It means perspective. Not every solar storm will coincide with atmospheric instability. Not every cold outbreak will. Whether lessons are actually absorbed, not just acknowledged. After every major disaster, reports are written, panels are formed, and promises are made. Yet the underlying frameworks often remain unchanged. The same assumptions quietly return, the same boundaries are redrawn, and the same blind spots persist. The danger is not ignorance. It's familiarity. Familiar explanations feel safe, even when they are incomplete. In the months following the freeze, scientific discussions continued largely out of public view. Papers were drafted, data was reviewed. Researchers debated whether the correlations observed were meaningful or coincidental. Some argued strongly that linking space weather to surface conditions risks confusing correlation with causation. Others countered that refusing to investigate such links risks missing emerging vulnerabilities. Both sides had valid points, and that tension is precisely where progress usually begins. What complicates matters further is that Earth's environment is entering a period of increased variability. Climate systems are no longer operating within the historical ranges that shaped our models. Arctic amplification is reducing temperature gradients that once stabilized circulation. Jet streams are becoming more erratic. Blocking patterns are lasting longer. Extremes are persisting beyond expected durations. These changes do not create new physics, but they do change how existing physics plays out. In such a context, the question shifts again. It becomes less about whether weather can influence surface conditions, and more about when such influence becomes noticeable. At what point does a previously negligible interaction become relevant? At what point does the atmosphere's sensitivity cross a threshold where timing effects matter more than magnitude? These are not easy questions to answer, and they resist simple experiments. But they are questions that can no longer be ignored, because the cost of being wrong has increased. A forecasting error today does not just mean inconvenience. It can mean lives disrupted, economies strained, and trust eroded. One of the most promising areas of research focuses on coupling strength. Scientists are trying to quantify how strongly different atmospheric layers communicate under various conditions. During calm periods, coupling is weak. Disturbances remain localized. During extreme periods, coupling intensifies. Energy and momentum transfer becomes more efficient. Small disturbances can propagate farther and faster than expected. If coupling strength increases during instability, then external influences naturally gain importance, not because they dominate, but because they arrive at a moment when the system is listening more closely. This idea reframes the role of space, weather entirely. It is not a driver. It is a signal injected into a receptive system. This perspective also explains why such connections are hard to detect statistically. They do not produce consistent outcomes. They do not leave clean signatures. They only matter when timing aligns, and timing alignment is rare by definition. But rarity does not mean irrelevance. Earth's most damaging events are rare, yet their impact defines policy, infrastructure, and risk management. The freeze exposed another critical issue. Preparedness is often based on averages. Design standards assume historical norms. Emergency plans assume gradual escalation. When events arrive faster than those assumptions allow, response lags behind reality. Integrating space weather into risk awareness could offer additional early warning, not of specific outcomes, but of heightened vulnerability windows. Imagine a future where forecasters don't just say conditions are favorable for extreme weather, but that the system is particularly sensitive in the coming days, where heightened solar activity is not treated as irrelevant noise, but as a contextual factor that increases uncertainty. That kind of awareness does not guarantee prevention, but it buys time. And time, in emergencies, is everything. This does not require dramatic changes overnight. It requires interdisciplinary thinking. Meteorologists talking to space physicists, modelers sharing assumptions, data streams being aligned rather than siloed. These are slow cultural shifts, but they are already beginning in quiet ways. The resistance will not disappear, nor should it. Skepticism keeps science honest. But skepticism should fuel investigation, not dismissal. The goal is not to prove a predetermined conclusion. The goal is to understand the system as it actually behaves, not as we wish it behaved. The freeze was a reminder that Earth operates as an integrated whole. Boundaries we draw are tools, not truths. When those tools begin to fail, clinging to them becomes a liability. As we move deeper into this story, the focus narrows further. We will examine specific case studies, patterns observed across decades, and moments where space and atmosphere appear to have spoken at the same time, not to claim certainty, but to understand probability, not to predict the exact shape of the next crisis, but to recognize when conditions are quietly aligning. Because the most dangerous events are not always the strongest ones. They are the ones that arrive when we least expect them, through pathways we thought didn't exist. Those pathways are difficult to see precisely because they don't announce themselves. They form slowly, invisibly. At the intersections of systems, we prefer to study in isolation. By the time their effects become obvious, the window for prevention has usually closed. That is why understanding patterns matters more than predicting single events. Patterns reveal vulnerabilities long before outcomes are locked in. When researchers began reviewing historical records with this broader lens, they noticed something subtle but intriguing. Periods of heightened geomagnetic activity often coincided with unusual atmospheric behavior, not consistently, not predictably. Role in shaping mid-latitude weather. Disturbances there can have far-reaching consequences. Another theme involves thresholds. Atmospheric systems often tolerate stress up to a point, then reorganize abruptly. These reorganizations are not gradual. They resemble phase changes. A circulation pattern holds, then suddenly breaks. When that happens, even small external influences can shape the outcome. The timing of a disturbance may matter more than its strength. This helps explain why many extreme events feel sudden, even when scientists knew the risk existed. The system didn't slowly evolve into danger. It crossed a line, and that line is difficult to locate in advance. The freeze followed this pattern. Warning signs existed, but they did not point to certainty until it was too late. The system appeared stable, then rapidly wasn't. Understanding whether space-driven energy injections can help push systems across such lines is not about assigning blame. It's about improving anticipation. Anticipation is the difference between disruption and disaster. When systems fail slowly, humans adapt. When they fail abruptly, damage multiplies. Modern societies are especially vulnerable to abrupt failure because they rely on tight coordination. Electricity, water, communications, healthcare, and transportation are interdependent. A shock to one quickly spreads to others. This is why the discussion matters beyond academic curiosity. It touches infrastructure design, emergency management, and policy. It raises questions about whether current risk assessments fully account for compounded vulnerabilities. It challenges the assumption that rare events remain isolated. Looking ahead, solar activity will continue to wax and wane. Climate trends will continue to load the atmosphere with energy. Arctic changes will continue to reshape circulation. None of these trends alone guarantees catastrophe. Together, they increase complexity, and complexity reduces predictability. The goal is not perfect prediction. That is impossible. The goal is situational awareness, knowing when multiple risk factors align, recognizing windows of heightened sensitivity, communicating uncertainty honestly rather than hiding it behind reassuring simplicity. This requires a cultural shift as much as a scientific one. It requires comfort with nuance. It requires admitting what we don't fully know. And it requires the humility to revise models when reality refuses to fit them. The freeze was not a failure of science. It was a reminder of its limits. Limits that can be expanded, but only if they are acknowledged. As this story continues, attention turns from theory to evidence, from possibility to precedent, from isolated cases to broader patterns that span decades and continents. Because once you step back far enough, the question is no longer whether the atmosphere and space interact. The question becomes how often they do so in ways that matter. Answering how often they matter requires stepping even further back, beyond any single storm, beyond any single decade. When researchers widen the lens, a different picture begins to emerge, one that doesn't rely on dramatic cause and effect claims, but on accumulation, small signals repeating over long periods, anomalies that don't dominate the data, but refuse to disappear from it either. Over the past century, scientists have cataloged periods of intense solar activity alongside major atmospheric disruptions. Not every solar maximum aligns with extreme weather, and not every extreme weather event follows a solar disturbance. That inconsistency is exactly why the topic remains controversial. But what stands out is not consistency, it's conditional relevance. The influence appears strongest when the atmosphere is already primed for change. Take sudden stratospheric warmings, for example. These events involve rapid temperature increases high above the surface that can weaken or reverse polar winds, often preceding severe winter weather at lower latitudes. They are rare, complex, and difficult to forecast. Some studies have noted that a subset of these events coincides with heightened geomagnetic activity. Not always, not predictably, but often enough to suggest the relationship is not random noise. The same pattern appears with jet stream disruptions. The jet stream is a high-altitude river of wind that helps regulate temperature distribution across continents. When it flows smoothly, weather patterns are relatively stable. When it becomes wavy or fragmented, extremes can persist. Heat waves linger, cold snaps plunge south, storms stall. Researchers have observed that during certain periods of increased solar disturbance, jet stream behavior becomes more erratic. Again, this does not imply control. It implies sensitivity. Sensitivity is the key concept here. The atmosphere does not need to be pushed hard to change. It needs to be pushed at the wrong moment. That moment is defined by internal conditions, temperature gradients, moisture distribution, background circulation. External inputs only matter when they coincide with internal vulnerability. This reframing resolves a long-standing debate. Critics are right when they say solar energy is too weak to drive weather. Proponents are right when they say timing effects can matter. Both can be true at the same time. The sun does not power storms. It may, under rare conditions, influence when they begin or how quickly they intensify. Understanding that distinction is crucial because it shifts focus away from dramatic claims and toward practical implications. If space-driven disturbances can accelerate atmospheric transitions, even occasionally, then monitoring those disturbances becomes part of situational awareness, not prediction. Awareness. Awareness changes how uncertainty is handled. Instead of asking whether a storm will happen, the question becomes how fragile the system currently is. Instead of treating solar activity as a relevant background and toward consequences, away from whether a connection exists, and toward what ignoring that possibility might cost. Because the real risk is not that scientists are wrong about space weather. The real risk is that they are partly right, and we fail to act on it. And when the next alignment occurs, when internal instability meets external disturbance, the question won't be whether we can explain it afterward. It will be whether we were paying attention beforehand. The uncomfortable truth is that systems don't collapse when they are weak. They collapse when they appear stable. Stability creates confidence. Confidence reduces caution, and reduced caution narrows the margin for error. By the time warning signs become obvious, the system is already too far into failure to turn back easily. That pattern has repeated across history. In financial markets, in ecosystems, in power grids, and increasingly, in the atmosphere itself. What made the freeze so disruptive was not simply the cold. It was the speed at which normal expectations stopped applying. In the days before the event, most signals suggested stress, not catastrophe. Forecast models hinted at instability, but nothing outside the range of past experience. Infrastructure operators prepared for winter demand, not system-wide strain. Emergency planners expected localized disruption, not cascading failure across multiple states. Everyone was operating inside familiar boundaries, and then those boundaries shifted all at once. The atmosphere reorganized faster than response systems could adapt, and once that reorganization began, it unfolded with a momentum that human planning simply could not match. Here is where the larger pattern begins to matter. Rapid atmospheric shifts are becoming more common in a warming world. Temperature contrasts are changing. Ocean heat content is rising. Moisture availability is increasing. These factors load the system with energy, but not in smooth, predictable ways. Instead, they create tension, stored potential that can be released suddenly when circulation patterns change. Think of it like a stretched spring. The more tension it holds, the less force is required to make it snap into a new position. Now imagine that moment of tension coinciding with an external disturbance, not a force large enough to dominate the system, but one capable of nudging it at precisely the wrong time. This is the scenario some researchers are beginning to take seriously, not because it overturns meteorology, but because it complements it. Internal instability sets the stage. External energy can influence the timing. Timing determines impact. This idea becomes even more significant when we consider how modern forecasting works. Models are excellent at identifying gradual trends. They are less reliable when systems cross thresholds. Those thresholds often appear invisible until they are crossed, because the variables that define them interact in nonlinear ways. Add an external input, like a surge of energy altering upper atmospheric dynamics, and the threshold may be reached sooner than expected. The forecast isn't necessarily wrong. It's late, and lateness, in extreme weather, is costly. Hours matter. A single day of additional warning can mean the difference between controlled shutdowns and chaotic failure, between preventative measures and emergency rescues, between inconvenience and tragedy. That is why even subtle influences deserve attention, not because they guarantee disaster, but because they may compress the timeline between stability and crisis. Another factor rarely discussed outside specialist circles is how interconnected critical infrastructure has become. Power grids depend on precise load balancing. Water systems depend on electricity. Communications depend on both. Transportation depends on all three. When one system fails abruptly, others follow. This is known as cascading failure, and it is the defining risk of modern societies. Extreme weather doesn't need to destroy everything directly. It only needs to push one vulnerable system past its limit. During the freeze, that vulnerable system was energy. Demand surged while supply faltered. Equipment not designed for prolonged cold began to fail. As generation dropped, rolling outages began. But rolling outages require coordination and control. When systems are overwhelmed too quickly, controlled outages become uncontrolled collapse. Water treatment plants lost power. Pipes froze and burst. Roads became impassable. Emergency services struggled to reach those in need. What began as a meteorological event became a systemic crisis. This cascade is what turns scientific nuance into real-world consequence. Whether or not space weather played any role in the timing of the atmospheric shift, the outcome revealed how thin the buffer has become between normal operations and widespread disruption. That buffer used to be measured in days. Now it may be measured in hours, and any factor that reduces warning time, even slightly, has amplified significance. There is another layer to this story that rarely reaches public discussion: perception. When extreme events are framed as isolated anomalies, recovery focuses on rebuilding what existed before. But if those events are signals of increasing system sensitivity, rebuilding the same way may simply reset the stage for the next failure. Understanding interconnected risk changes how resilience is designed. It shifts the goal from resisting known threats to adapting to uncertain ones. Scientists studying these questions are not searching for dramatic revelations. They are looking for subtle statistical shifts, small but consistent signals that indicate the system is behaving differently than it used to. That work is slow, cautious, and often contested. But it is underway, driven by the recognition that Earth's environment is no longer operating within the historical ranges that shaped our expectations. As solar activity rises and falls over the coming years, more opportunities will arise to study these interactions in real time. Cause and effect are rarely clean. Influences overlap. Timelines blur. And by the time a chain of events reveals its full shape, we are usually standing in the middle of its consequences, not observing safely from the outside. The freeze exposed that reality with uncomfortable clarity. It was not simply a weather story. It was a systems story, a demonstration of how tightly coupled modern life has become to environmental stability we can no longer take for granted. One of the most striking aspects of the event was how quickly confidence unraveled. In the early stages, forecasts spoke in probabilities and ranges. There was uncertainty, but also reassurance that extreme outcomes were unlikely. Then, almost abruptly, those ranges shifted. Worst-case scenarios moved from the edges of possibility toward the center. Decision-makers had to react not to a gradual change, but to a sudden redefinition of risk. That kind of shift is disorienting, both scientifically and socially. It challenges trust in models, even when those models performed as designed. The deeper issue is that models are built on history, and history is becoming a less reliable guide. When background conditions evolve, warmer oceans, altered circulation patterns, a changing magnetic field, the baseline shifts. Relationships that once held steady begin to wobble. Feedback loops strengthen or weaken in ways that are difficult to quantify in advance. In that environment, rare alignments of factors can produce outcomes that feel unprecedented, even if each ingredient is familiar on its own. Consider how we define rare. In a stable climate, rare events might occur once in several decades. Infrastructure is built with those probabilities in mind. But when the system itself is changing, the meaning of rare shifts as well. Events that once sat at the edge of possibility may move closer to the center, not because the physics of the atmosphere have changed, but because the conditions feeding into that physics have. Add an external disturbance at the wrong moment, and the boundary between rare and plausible blurs even further. This is where space weather re-enters the conversation, not as a dominant force, but as a complicating one. Solar activity operates on cycles we understand broadly, but cannot predict precisely. Magnetic disturbances arrive with little warning beyond the travel time of charged particles. Most pass with minimal impact beyond beautiful auroras and minor technological disruptions. But in a world where atmospheric systems are already closer to instability, even background variability can matter more than it once did. Think of it like turbulence on an airplane. In calm skies, small bumps barely register. In rough air, the same bumps can throw the cabin into chaos. The force hasn't changed, the conditions have. Earth's atmosphere may be entering a period where it behaves more like rough air than calm skies. That doesn't mean constant disaster. It means greater sensitivity to timing and overlap between influences. Another reason this matters is psychological. Humans are good at adapting to gradual change. We are less good at preparing for sudden transitions that break from recent experience. When an event exceeds expectations, the instinct is often to label it an outlier and move on. That response protects short-term confidence, but it can delay necessary adjustments. If extreme events are becoming more sensitive to multi-layered influences, resilience planning must expand accordingly. This doesn't require rewriting textbooks overnight. It requires expanding the conversation. Meteorologists, climate scientists, and space physicists each hold pieces of a larger puzzle. Historically, those pieces were studied separately because the connections seemed weak. Now, those connections may be strengthening, not uniformly, not predictably, but enough to deserve attention. Bridging those fields is less about proving dramatic new theories and more about reducing blind spots in risk awareness. Blind spots are dangerous not because they guarantee failure, but because they limit options. If a system appears stable until the moment it fails, response becomes reactive rather than proactive. Early signals, even uncertain ones, create space for precaution. They allow grid operators to prepare for unusual demand, emergency services to preposition resources, and communities to take protective measures. That margin of preparation can turn a crisis into a challenge rather than a catastrophe. During the freeze, that margin was thin. By the time the scale of the event became clear, millions were already exposed to dangerous conditions. The lesson is not that science failed, but that complexity outpaced expectation. When multiple layers of a system shift at once, outcomes can accelerate beyond familiar timelines. Recognizing that possibility is the first step toward adapting to it. Looking forward, the most important developments may not be dramatic breakthroughs, but quiet integrations. Space weather alerts considered alongside atmospheric forecasts, upper atmospheric data feeding into long-range models, risk assessments that account for compounding influences rather than treating them independently. Each step may seem small, but together they widen the window of awareness. And awareness, ultimately, is what determines resilience. We cannot prevent every extreme event. We cannot control the sun, the oceans, or the chaotic dance of atmospheric circulation. But we can improve how we interpret the signals those systems send. We can become better at recognizing when the background noise of variability is rising, when the system feels different, even if we cannot yet explain why, because the next crisis will not arrive with a label announcing its complexity. It will look, at first, like just another anomaly, just another forecast that seems slightly uncertain, just another set of data points that don't quite fit expectations. The difference between disruption and disaster may lie in whether we have learned to take those subtle signals seriously. The freeze illustrated how quickly that lag can grow. Conditions escalated faster than infrastructure, and emergency systems were designed to handle. The cold itself was not the only problem. It was the mismatch between how fast the environment changed and how fast human systems could respond. That mismatch is where risk concentrates, and it is precisely the kind of mismatch that can be amplified when multiple influences converge. This brings us back to the idea of layered vulnerability. Climate trends are increasing baseline stress in the atmosphere. Polar regions are warming faster than the global average, altering the gradients that help anchor large-scale circulation. Oceans are storing more heat, adding energy and moisture that can be released in sudden bursts. At the same time, technological and societal systems are becoming more tightly coupled, with less redundancy than in the past. Each layer by itself might be manageable. Together, they form a landscape where small disturbances can have outsized effects. Space weather fits into this landscape not as a dominant force, but as an intermittent one. Most of the time, it operates in the background, influencing satellites and communications more than surface conditions. But during periods of strong solar activity, its footprint expands. The upper atmosphere heats, electrical currents intensify, and energy moves through pathways that are usually quiet. If the lower atmosphere is already near a threshold, these additional inputs may help determine when that threshold is crossed. This is not a deterministic relationship. There is no simple rule that a solar storm equals a surface disaster. Instead, it is a probabilistic one. Space-driven disturbances may slightly increase the chance that an unstable atmospheric configuration shifts sooner rather than later. In a stable climate, that timing shift might go unnoticed. In a stressed climate, it can change the difference between a manageable event and a cascading crisis. Understanding this requires a shift in mindset from single-cause thinking to network thinking. Rather than asking, what caused this storm? The more useful question may be, what combination of factors made this storm unfold the way it did? That approach accepts that extreme events are rarely the product of one driver. They emerge from the interaction of many, some internal, some external, some slow-moving, others sudden. Network thinking also changes how preparedness is framed. Instead of designing systems for the most likely scenario, resilience planning must consider how unlikely factors can align. This doesn't mean preparing for every imaginable catastrophe. It means identifying where systems are most sensitive to rapid change and building flexibility there. It means ensuring that power grids can handle temperature swings outside historical norms, that communication systems remain functional during geomagnetic disturbances, and that emergency planning accounts for compound failures rather than isolated ones. Another critical piece is communication. As scientific understanding grows more nuanced, conveying that nuance to the public becomes more challenging. People want clear answers. What caused this? And will it happen again? But in complex systems, honest answers often involve uncertainty and conditional probabilities. Communicating that without eroding trust requires transparency about limits and an emphasis on preparedness over prediction. The freeze became a story of surprise partly because the narrative focused on what went wrong rather than on why systems were vulnerable in the first place. Reframing future discussions around vulnerability and sensitivity rather than blame could help shift attention toward adaptation. It moves the conversation from reacting to past events toward anticipating future ones. There is also an opportunity here for scientific collaboration. The boundaries between disciplines were drawn for practical reasons, but nature does not observe those boundaries. Integrating data from space weather monitoring, atmospheric modeling, oceanography, and climate science offers a more complete picture of the conditions that precede extreme events. That integration is complex and resource-intensive, but the potential payoff lies in earlier recognition of risk windows. Risk windows are not predictions of disaster. They are periods when the system is more sensitive than usual, when multiple stressors overlap. During such windows, even moderate disturbances can have amplified effects. Identifying them in advance allows for precautionary measures that are far less costly than emergency response after the fact. As we look ahead, the pace of environmental change suggests that these windows may become more frequent, not because any single driver is becoming overwhelming on its own, but because interactions are becoming more common. A warmer atmosphere holds more energy. A changing Arctic alters circulation patterns. A fluctuating sun continues its cycles. A gradually weakening magnetic field modifies how energy from space is distributed. None of these guarantees crisis. Together, they increase complexity. Complexity is not inherently negative. It is a feature of dynamic systems, but it demands humility. It reminds us that models are approximations, that forecasts carry uncertainty, and that resilience depends on flexibility as much as precision. The lesson of the freeze is not that we are powerless. It is that we must be attentive to signals that fall outside traditional expectations. Because the next time the atmosphere reorganizes itself, the clues may once again appear quietly at first, in subtle data shifts, in unusual upper atmospheric behavior, in patterns that don't quite match the past. Whether those clues translate into timely preparation or retrospective analysis will depend on how willing we are to see Earth as an interconnected system, where influences from above and below can meet in ways we are only beginning to understand. Seeing Earth as an interconnected system changes more than just scientific models. It changes how responsibility is understood. When events are framed as isolated, imagine a future scenario where a region is already dealing with a prolonged heat wave that strains power supplies. At the same time, a strong solar storm disrupts satellite communications and induces currents in transmission lines. Neither factor alone might cause a blackout. Together, they could push the grid past its limits. This is the nature of compound risk. Outcomes shaped not by a single extreme, but by the overlap of multiple moderate ones. The freeze was an example of that overlap. A vulnerable atmospheric configuration met an already stretched infrastructure. Whether or not space, weather played a role in the timing, the broader lesson remains. Systems designed for isolated extremes struggle when extremes stack. Preparing for that reality requires moving beyond single-hazard thinking. It also requires accepting that uncertainty will remain a permanent feature of environmental risk. There will always be limits to prediction, especially in systems that are changing faster than historical data can fully capture. But uncertainty does not have to mean helplessness. It can motivate flexibility, building systems that can bend without breaking, that can operate under a wider range of conditions than expected. In practical terms, that might mean diversifying energy sources so that no single failure cascades through the entire grid. It might mean designing buildings and infrastructure to tolerate broader temperature swings. It might mean improving communication between scientific communities so that signals from one domain are not ignored by another. None of these steps eliminate risk. They reduce sensitivity to it. There is also a cultural component. Societies accustomed to stable patterns can be slow to adjust to volatility. People build expectations based on lived experience, and when those expectations are repeatedly disrupted, trust can erode. Transparent communication about uncertainty and interconnected risk can help manage that transition. It prepares communities not just for specific events, but for a future in which surprises are more common. From a scientific perspective, the path forward involves refining how we observe and model Earth as a whole system. Satellites now provide continuous monitoring of the Sun, the magnetosphere, and the upper atmosphere. At the same time, ground-based networks track weather, ocean conditions, and climate trends. The challenge is not collecting data. It is integrating it in ways that reveal patterns across scales. As computing power increases and interdisciplinary collaboration grows, models will become better at representing these cross-layer interactions. They may never predict exactly when a tipping point will be reached, but they can improve our understanding of when the system is approaching one. That awareness can inform precautionary decisions, even in the absence of certainty. Ultimately, the story of the freeze is not about proving a single connection between space and weather. It is about recognizing that Earth systems are entering a period where interactions matter more than ever. The comfortable separations that once defined scientific disciplines are becoming less reflective of reality. Weather does not occur in isolation from climate. Climate does not evolve in isolation from oceans. And the atmosphere does not exist in isolation from space. The implications extend beyond any single storm. They touch how cities are built, how energy is managed, how emergencies are planned, and how science itself is organized. The world is not becoming more dangerous in a simple linear way. It is becoming more interconnected, more sensitive to timing, and more prone to cascading effects when multiple stresses align. That may sound unsettling, but it also offers an opportunity. Greater understanding of interconnected systems allows for smarter resilience. Instead of reacting to each new crisis as an unpredictable anomaly, societies can prepare for a landscape where variability itself is the norm. Preparation in this context means flexibility, redundancy, and communication across boundaries that once seemed unrelated. In the end, the most important lesson is not about the past storm, but about perspective. If we continue to view extreme events through narrow lenses, we will always be surprised by how they unfold. If we broaden our view to include the full web of influences shaping our planet, surprises will still occur, but we may be better positioned to absorb them. Because the question is no longer whether another extreme event will come. It is whether, when the next convergence of stresses begins to form, quietly, across layers of atmosphere and space, we will recognize the pattern early enough to respond with foresight instead of hindsight. Foresight begins with a simple but uncomfortable admission. The world we built our expectations on is no longer the world we live in. The climate baseline has shifted. The behavior of large-scale circulation patterns is evolving. The protective magnetic environment surrounding Earth is slowly changing. None of these transformations announce themselves dramatically on a daily basis. They unfold in background trends, subtle drifts, and small deviations that only become obvious when viewed over years or decades. Yet when those slow changes intersect with short-term extremes, the results can feel sudden and shocking. One of the most important adjustments we can make is to rethink what normal means. Normal used to be a stable reference point, a range within which most variability occurred. Today, normal is moving. It is a sliding scale influenced by warming oceans, melting ice, and shifting energy balances in the atmosphere. When the baseline moves, the same disturbance can produce different outcomes than it did in the past. A circulation wobble that once caused a brief cold spell might now unleash a prolonged outbreak because background conditions have changed. This moving baseline is what makes timing so critical. Systems that appear stable may, in reality, be closer to their limits than historical comparisons suggest. Add a burst of external energy at the wrong moment, and the system may cross a threshold. How moderate hazards can align. This includes ensuring backup systems do not share the same vulnerabilities as primary ones, diversifying supply routes, and strengthening communication between sectors that traditionally operate independently. It also means investing in observation systems that watch the planet as a whole, continuous monitoring of solar activity, geomagnetic conditions, atmospheric circulation, ocean heat content, and cryosphere changes provides the raw material for identifying patterns of overlap. The goal is not to predict exact outcomes, but to recognize when multiple stress indicators are rising at the same time. Such recognition could lead to the concept of heightened sensitivity periods, windows when the Earth system is more prone to abrupt change. During these periods, precautionary measures could be taken even if no single forecast guarantees disaster. Power grids might operate with larger safety margins. Emergency services might increase readiness. Communication systems might be tested and reinforced. These steps are relatively low cost compared to the damage caused by being caught off guard. Another key element is education, not just for scientists, but for the public and decision makers. Understanding that uncertainty is an inherent part of complex systems helps shift expectations. Today, those distinctions blur. Slow changes set the stage. Fast changes trigger responses, and influences from outside the atmosphere may occasionally alter the timing. The clocks are no longer independent. They tick together. This does not mean living in constant expectation of disaster. It means adjusting to a world where variability is higher and margins are thinner. In such a world, awareness becomes a form of resilience. Knowing that systems can shift quickly encourages precaution when signals begin to align. It encourages decision-makers to act earlier rather than later, even when certainty is incomplete. The role of communication grows more important in this context. Clear explanations of risk windows, uncertainty ranges, and system sensitivity can help communities prepare without panic. The goal is not to alarm, but to inform, to replace the illusion of perfect predictability with the reality of informed adaptability. Technology will play a role as well. Advances in satellite monitoring, data assimilation, and high-resolution modeling are already improving our ability to see the planet as an integrated whole. Artificial intelligence systems are beginning to identify patterns across vast datasets that human analysts might miss. These tools will not predict every shift, but they can highlight when multiple indicators are trending in the same direction. At the same time, resilience depends on human decisions. Investments in infrastructure, emergency planning, and scientific research shape how well societies absorb shocks. The lesson of interconnected risk is not that we are powerless. It is that preparedness must evolve as understanding evolves. Looking back, the freeze was a moment when several layers of vulnerability aligned. Atmospheric instability met infrastructural fragility. Rapid change outpaced response. Whether or not influences from space contributed to the timing, the event demonstrated how quickly modern systems can be pushed beyond their comfort zones. Looking forward, the question is not whether such alignments will happen again. They will. The question is whether we recognize them earlier, interpret their signals more broadly, and design our systems with enough flexibility to absorb their impact. That requires seeing Earth not as a collection of separate parts, but as a dynamic whole, a planet where sky, surface, and space are linked in ways we are only beginning to fully understand. In that understanding lies a quieter kind of preparedness, not the promise of perfect forecasts, but the confidence that comes from expecting complexity, the willingness to plan for overlap, to build margins into systems that once ran too close to the edge, and to treat unusual signals not as curiosities, but as potential clues. Because the future will not unfold along the lines we drew in the past. It will be shaped by interactions, timing, and sensitivity, by the subtle choreography of forces, both familiar and distant. And the more we learn to watch that choreography as a whole, the better prepared we will be when the next shift begins, quietly at first, before the world realizes just how much has changed. The consequences of ignoring weak signals rarely arrive all at once. They accumulate quietly, stacking subtle vulnerabilities on top of one another until a system that once seemed robust begins to feel brittle. Long before lights go out or pipelines freeze, before airports shut down and supply chains stall, there are warning signs moving through spreadsheets and satellite feeds. Numbers that drift slightly outside historical envelopes. Magnetic fluctuations that last a little longer than expected. Atmospheric models that require more last-minute corrections than usual. Individually, none of these raise alarms. Together, they form a pattern that only becomes obvious in hindsight. And hindsight, in complex systems, is always expensive. Picture the scene inside a space weather forecasting center during a period of elevated solar activity. Walls glow with real-time data streams. Particle counts rising, magnetic field lines bending, radiation sensors registering spikes. Engineers track satellite trajectories through vulnerable regions of near-Earth space. Operators quietly shift spacecraft into safe modes. At the same time, hundreds of miles below, meteorologists watch a different set of screens. Pressure gradients tightening over the Arctic, wind fields growing unstable, long-range models beginning to diverge instead of converge. Two worlds, two scientific traditions, two types of risk assessment unfolding in parallel. Most days, they remain separate, but on rare occasions, those screens begin to change in synchrony. And that is when the uncomfortable questions return. Because what matters is not whether weather usually affects surface conditions. What matters is whether it can matter sometimes under just the wrong combination of circumstances. A system already stressed does not require a dramatic shove. It requires timing. A small nudge at the wrong moment can redirect enormous energy already stored within the atmosphere. That principle is not controversial in physics. It is foundational. Avalanche forecasters know it. Structural engineers design for it. Economists watch for it in markets. In nonlinear systems, stability is often an illusion maintained only until the final variable shifts. The modern world has become exceptionally good at optimizing for normal conditions. Power grids run close to capacity to reduce waste. Transportation networks depend on precise scheduling. Supply chains stretch across oceans with minimal slack. These efficiencies deliver comfort and affordability, but they also reduce tolerance for surprise. When extreme cold arrives days earlier than expected, or when satellite disruptions complicate navigation and communication during an unfolding crisis, the margin for error collapses. What once would have been a difficult week becomes a cascading emergency. Not because any single failure was catastrophic on its own, but because several occurred simultaneously. This is where the conversation quietly moves away from scientific curiosity and into strategic necessity. Emergency planners increasingly speak in terms of compound risk, the overlap between unrelated-looking hazards that amplify one another when timing aligns. A winter outbreak during a routine year is disruptive. A winter outbreak during a stressed fuel supply is far worse. Add telecommunications interference, strained transformers, or compromised satellite positioning, and recovery slows dramatically. The question becomes less about attribution and more about readiness. Even if space-driven disturbances only influence surface systems occasionally, ignoring them entirely leaves blind spots in forecasting frameworks built for a simpler era. Some research groups are already responding to this complexity by redesigning how warnings are issued. Instead of focusing solely on expected outcomes, snowfall totals, wind speeds, temperature lows, they are experimenting with vulnerability indices, metrics that describe how sensitive the atmosphere and infrastructure appear at a given moment. These indices incorporate soil moisture, reservoir levels, grid load, atmospheric instability, and yes, sometimes indicators from the upper atmosphere. Not to claim a direct cause and effect relationship, but to highlight periods when uncertainty is elevated and resilience should be prioritized. That shift reflects a deeper change in how scientists are thinking about prediction itself. Traditional forecasting aims for specificity, where the storm will land, how cold it will get, how long it will last. In a more interconnected world, forecasters are learning to speak in probabilities of disruption, ranges of plausible futures rather than single deterministic tracks. That may feel less satisfying to the public, but it is often more honest. Complex systems rarely announce their tipping points with precision. They whisper first, through anomalies that only become obvious after the fact. And this is where the story becomes more unsettling, because the planet is entering a phase in which those whispers may be growing louder. Solar cycles continue their rhythms. Atmospheric circulation grows more erratic in a warming climate. Magnetic field variations subtly alter how energy from space is distributed around Earth. None of these operate in isolation. Each modifies the background state in which the others unfold. The result is not a world of constant catastrophe, but a world in which rare alignments may become slightly less rare and far more consequential when they occur. Consider how quietly that shift could manifest, not as a single headline-grabbing breakthrough, but as a series of after-action reports noting that forecasts were shortened again, that infrastructure struggled in unexpected ways, that recovery required more improvisation than planning frameworks anticipated. Each event is explained individually. Each is labeled unusual. Only later does a pattern begin to emerge, visible only when years of data are layered atop one another. And that is the danger of waiting for certainty in systems that reward anticipation. By the time every mechanism is fully mapped and every connection conclusively proven, the cost of being unprepared may already have been paid several times over. The goal is not to declare new culprits for extreme weather. It is to widen the lens through which vulnerability is assessed, to recognize that risks rarely arrive alone, and that resilience depends as much on flexibility as on prediction. What makes this moment different from past eras is the sheer scale of human dependence on delicate technological systems. Satellites guide aircraft across oceans. Timing signals synchronize financial networks. Weather models depend on space-based sensors. Power flows across continents in tightly coupled grids. When any one of these falters during an unfolding environmental crisis, the effects ripple outward faster than emergency managers can adapt. The modern world moves at the speed of electricity and data, and so do its failures. That realization is driving a new generation of interdisciplinary work. Engineers sitting alongside atmospheric scientists, space physicists collaborating with grid operators, climate modelers sharing simulations with disaster response agencies. The objective is not to create perfect forecasts. It is to build awareness of when multiple stressors may be aligning, and to design systems that degrade gracefully rather than collapse suddenly. Because the real lesson of that historic freeze was not confined to frozen roads or shattered pipelines. It was embedded in the timing, in how rapidly conditions changed, in how little warning some communities had before life-supporting infrastructure was pushed beyond design limits. Whether or not space-driven disturbances played any role in that sequence, the event exposed a world optimized for yesterday's risks and struggling to adapt to tomorrow's. And as we move closer to the final questions this story raises, The focus tightens even further, not on whether such overlaps can happen, but on what ignoring their possibility might cost in a century defined by interconnection. Because the next disruption may not announce itself with a single dramatic trigger. It may arrive as a convergence, a handful of moderate stresses aligning at precisely the wrong moment, quietly transforming a routine forecast into a national emergency before most people realize what has begun. And by the time the first lights flicker, the most important decisions may already be behind us. The unsettling truth is that most large-scale failures do not begin with catastrophe. They begin with assumptions, quiet, reasonable assumptions that hold true most of the time. Power systems assume seasonal demand curves will stay within historical bounds. Communication networks assume satellites will operate without interruption. Transportation planners assume storms will evolve slowly enough to allow rerouting and staging. Forecasting agencies assume atmospheric behavior will remain within the envelope defined by past decades. None of these assumptions are reckless. They are built on long records and careful engineering, but they share one vulnerability. They are optimized for a world where hazards arrive one at a time. When multiple pressures stack together, the math changes. A region facing deep cold draws extraordinary amounts of electricity for heating. Natural gas systems struggle as compressors freeze and wells slow production. Ice loads transmission lines, increasing mechanical stress just as electrical demand peaks. Now layer in subtle disruptions to satellite timing signals used for grid synchronization or radiation-induced sensor errors that complicate monitoring systems. Each individual strain might be manageable. In combination, they narrow the margin for recovery to almost nothing. Operators are forced to make rapid decisions with imperfect information, often while the very systems they rely on for situational awareness are being degraded. Inside control rooms, this convergence feels less like a single dramatic moment and more like a slow tightening. Alarms begin appearing in clusters instead of isolation. Forecasts that normally converge start to diverge. Backup systems activate earlier than expected. Engineers shift from optimization mode into survival mode, shedding load, isolating segments of the grid, rerouting power flows in ways rarely practiced outside of simulations. These are not the scenes most people imagine when they think of infrastructure failure. There is no explosion, no cinematic collapse. There is only a growing sense that events are outrunning procedures. What makes this especially difficult is that compound crises unfold across domains governed by different agencies, regulations, and professional cultures. Space weather forecasters speak in terms of geomagnetic indices and particle flux. Meteorologists talk about pressure anomalies and jet stream meanders. Grid operators track frequency stability and transformer temperatures. Emergency managers focus on shelters, fuel distribution, and medical capacity. Each group sees a piece of the picture. Few are trained to interpret all of it at once. Coordination improves after disasters, but during the early stages of unfolding events, information often moves more slowly than the systems themselves. This is why some researchers argue that the future of hazard prediction lies not in better single-discipline models, but in metamodels, frameworks that ingest outputs from many forecasting systems simultaneously and look for dangerous alignments rather than isolated extremes. These tools would not attempt to say, a blackout will occur at 3 p.m. on Thursday. Instead, they would flag periods when atmospheric volatility, infrastructure stress, and space environment disturbances are all trending upward together. The output would resemble a weather forecast for systemic fragility rather than for snowfall. Early versions of such approaches already exist in experimental form. Machine learning systems trained on decades of environmental and Infrastructure data are beginning to identify patterns that human analysts struggle to see, subtle combinations of variables that precede major disruptions more often than chance would suggest. These systems do not understand physics in the human sense. They simply notice that certain constellations of conditions tend to appear before trouble follows. Used carefully, they could act as an additional layer of situational awareness, prompting officials to prepare earlier, stage resources, or delay risky operations during sensitive windows. But technology alone cannot resolve a challenge rooted in institutional habits. Organizations evolve around specific missions, budgets, and regulatory frameworks. Expanding the scope of risk assessment requires changes in training, communication channels, and even professional identity. It asks meteorologists to care about solar indices, space physicists to think about gas pipelines, engineers to consider atmospheric coupling, and emergency planners to weigh uncertainties that do not fit neatly into existing playbooks. That kind of integration moves slowly in any bureaucracy, yet the pace of environmental change is not waiting. The deeper issue beneath all of this is philosophical as much as technical. For decades, hazard management has been guided by a search for dominant causes. What triggered the blackout? What produced the storm? What failure cascaded first? These questions are important for accountability and engineering improvement, but in a world shaped increasingly by interaction effects, they may no longer capture the full story. Sometimes the most important factor is not which domino fell first, but how many dominoes were already leaning. This perspective reframes how disasters are remembered. Instead of treating each extreme event as an outlier, it encourages analysts to view them as stress tests, moments when the hidden structure of complex systems becomes visible. Which safeguards worked, which assumptions failed, which interdependencies were underestimated, which warning signs were present but dismissed as noise. Over time, those stress tests accumulate into a map of vulnerability far more informative than any single incident. And that is precisely why the question raised by that historic freeze refuses to fade away, not because it definitively proves that energy from space helped trigger a polar outbreak, but because it highlights how tightly coupled modern life has become to layers of the environment most people never think about. The upper atmosphere, once relevant mainly to radio operators and aurora enthusiasts, now matters to GPS navigation, satellite imagery, climate monitoring, and emergency coordination. Disturbances there ripple downward through technological systems, long before they might ever influence clouds or winds. Ignoring that reality is no longer an option. There is also a generational dimension to this shift. Engineers and planners trained decades ago built systems for a climate that changed slowly, and for space weather risks considered rare curiosities. Younger scientists are entering fields where volatility is the baseline assumption rather than the exception. Their models incorporate wider error bars. Their planning scenarios include overlapping crises. Their research questions are less about whether coupling exists at all, and more about how strong it becomes under extreme conditions. That change in mindset is subtle, but consequential. It moves policy discussions away from promises of complete control and toward strategies of adaptation, designing grids that can island themselves when stressed, satellites that can ride out radiation storms, forecasting centers that exchange information across disciplines in real time, emergency systems that mobilize resources before impacts become obvious to the public. These measures are not glamorous. They rarely make headlines until after they succeed, but they represent a quiet form of progress that only becomes visible when disaster does not strike as hard as it could have. Still, even the most flexible systems cannot eliminate uncertainty. The Earth remains a non-linear machine powered by oceans, atmosphere, molten iron, and a variable star 93 million miles away. Interactions among those components will always produce surprises. The best societies can hope for is not perfect foresight, but shorter reaction times, wider safety margins, and a willingness to revise assumptions before reality forces the issue. And this brings us to the most uncomfortable part of the story, the cost of delay. Every year that frameworks remain siloed is another year in which overlapping risks may go unrecognized. Every near miss that is written off as coincidence is a missed opportunity to refine understanding. Every post-disaster report that focuses narrowly on one trigger risks, overlooking the broader pattern that made the system fragile in the first place. Because the next crisis may not resemble the last. It may arrive as a heat wave instead of a freeze, a drought instead of a flood, a cyber disruption layered atop a geomagnetic storm, or a supply chain failure unfolding during a period of atmospheric instability. The specific hazards will differ. The structure of the vulnerability may not, and that is the thread running through this entire investigation. Not the search for a single dramatic culprit, but the recognition that in an interconnected world, timing is power. When stresses converge, even modest disturbances can reshape outcomes. When they do not, systems absorb shocks and move on. Understanding the difference between those two states, between resilience and fragility, may become one of the defining scientific and policy challenges of the coming decades. Because somewhere right now, the sun is releasing bursts of energy. The atmosphere is shifting in slow, restless waves. Magnetic fields are drifting. Infrastructure is aging. Demand curves are rising. Most of the time, these processes unfold independently, but occasionally their rhythms align. And when they do, the consequences are never confined to one layer of the planet. When those rhythms align, the warning rarely arrives as a siren. It arrives as a discrepancy, a sensor reading that does not quite match expectation, a model run that suddenly requires more adjustments than the one before it, a forecast briefing that includes more caveats than confidence. Engineers and scientists are trained to live with uncertainty, but they are also trained to filter noise from signal. The challenge is that in tightly coupled systems, the earliest signals often look exactly like noise. They flicker at the edges of datasets, easily dismissed unless someone is already looking for patterns that cross traditional boundaries. This is why the next phase of preparedness is increasingly focused on detection rather than prediction. Instead of asking only what the weather will do, researchers are asking how sensitive the system is right now, how much unused capacity exists in power networks, how stable the polar circulation appears relative to recent decades, how saturated soils are before another storm arrives, how energetic the near-Earth space environment has become. Each of these metrics describes a layer of vulnerability. When several drift toward extremes simultaneously, the risk landscape changes even if no single forecast looks catastrophic on its own. Some agencies are experimenting with what amounts to environmental dashboards, integrated displays that combine atmospheric outlooks, space weather alerts, infrastructure stress indicators, and supply chain resilience. Metrics. The idea is not to overwhelm decision makers with data, but to reveal alignment. A red flag in one domain may be routine. Red flags in 3 at once deserve attention. The difficulty lies not in building the technology, but in persuading institutions to trust tools that blur the lines between disciplines that have spent decades operating separately. The stakes of that integration become clearer when examining how rapidly crises now propagate through modern societies. A transformer failure is no longer a local inconvenience. It can ripple through regional grids. A satellite malfunction does not merely affect researchers. It disrupts shipping routes, financial transactions, and emergency communications. A stalled highway system during an extreme cold snap delays fuel deliveries precisely when heating demand peaks. None of these cascades require dramatic new physics. They emerge from connectivity. The same networks that make modern life efficient also transmit stress at remarkable speed. This acceleration is altering the timeline of disaster response. Historically, communities often had days to mobilize before the worst impacts arrived. Today, the window between early warning and systemic strain is shrinking. When forecasts shift abruptly, or when infrastructure begins failing earlier than expected, emergency managers are forced to compress decisions that once unfolded over weeks into a matter of hours. That compression magnifies the cost of misjudgment. Acting too late is obvious. Acting too early is politically and economically risky. Navigating that tension requires confidence not only in forecasts, but in the broader assessment of systemic fragility. And fragility is not evenly distributed. Older infrastructure built to historical climate norms tends to crack first. Regions dependent on single energy sources or long supply chains have fewer options when disruptions occur. Communities already stretched by economic or health stresses absorb shocks less easily than those with surplus capacity. These social dimensions intertwine with physical systems, shaping how environmental disturbances translate into human consequences. A cold wave that is inconvenient in one place becomes deadly in another. This is where the conversation circles back to communication. The public is accustomed to hearing about isolated hazards, a storm, a heat wave, a solar flare. What is far harder to convey is conditional risk, the idea that an event becomes dangerous not solely because of its own intensity, but because of what else is happening at the same time. Explaining that nuance without causing alarm is one of the hardest tasks in modern risk management. Too much reassurance breeds complacency. Too much speculation erodes trust. Finding the balance requires transparency about uncertainty and humility about the limits of knowledge. Some scientists argue that society is already in the middle of a quiet transition toward that mindset. Weather forecasts now routinely include probabilistic cones instead of single tracks. Seasonal outlooks discuss ranges rather than certainties. Space weather agencies publish watch and warning scales that mirror those used for hurricanes. These tools acknowledge that prediction is never perfect, but preparation can still be calibrated. The next step is linking those probabilistic worlds so that elevated geomagnetic activity does not sit in a separate silo from atmospheric instability, but feeds into a broader picture of situational awareness. There is an uncomfortable implication hidden inside that proposal. If systems are increasingly sensitive to timing and overlap, then the number of potential high-impact scenarios multiplies. Planning for each individually becomes impossible. Resilience in that context is not about preparing for every conceivable disaster. It is about strengthening the underlying structures so that they bend rather than snap when surprises occur. Redundancy in energy systems, modular grids, diverse communication pathways, stockpiles of critical supplies, training exercises that simulate compound events instead of single hazards. These measures do not prevent storms or solar eruptions. They change how much damage those forces can ultimately inflict. Viewed through that lens, the freeze that sparked this investigation becomes less a singular anomaly and more a preview of the kinds of stress tests modern societies are likely to face again. Rapid shifts, narrow warning windows, infrastructure operating at the edge of design limits, conflicting signals from different forecasting communities, public confusion about what to expect, political pressure to provide certainty where none exists. All of those elements are likely to recur, even if the specific meteorological details differ. And yet, there is a paradox at the heart of this story. The more interconnected and technologically sophisticated societies become, the more tools they possess to detect subtle signals before disaster unfolds. Satellites watch the sun continuously. Ground-based observatories monitor magnetic fluctuations. Weather radars scan storms minute by minute. Smart grids report load changes in real time. Supply chains are tracked digitally from factory floor to front door. The raw material for early warning has never been richer. The challenge lies in synthesis, turning torrents of specialized data into coherent insight. That synthesis is not merely a technical problem. It is cultural. It requires institutions to share information they once guarded, to trust analyses produced outside their own fields, to accept alerts that arrive wrapped in uncertainty rather than certainty. It asks decision-makers to act when probabilities shift, not only when disasters are already visible on the horizon. Those habits are difficult to cultivate in systems built around accountability after the fact rather than precaution before it. Still, the direction of change is unmistakable. Joint task forces linking atmospheric scientists and space weather experts are becoming more common. Infrastructure planners are consulting climate projections instead of relying solely on historical averages. Emergency drills increasingly include multi-hazard scenarios. Academic journals publish more studies on cross-layer coupling and compound risk. These developments may not make headlines, but they signal a gradual realignment in how risk itself is conceptualized. And that realignment raises one final, unsettling question. If the future is defined less by isolated extremes and more by convergence, by the overlap of moderate stresses arriving at precisely the wrong moment, then the most dangerous events may be the ones that look ordinary right up until they are not. The storms that intensify faster than expected, the outages that spread farther than models predicted, the disruptions that ripple through systems assumed to be independent. By the time those patterns become obvious to everyone, the window for prevention may already be closing, which is why the most important work may be happening long before the next headline appears. Inside quiet laboratories, data centers, forecasting rooms, and planning meetings where scientists and engineers argue over graphs that only hint at what might be coming. Because in a world governed by timing, the difference between inconvenience and catastrophe is often decided days, or even hours, before the first visible sign of trouble. And the question that lingers after everything we have examined is not whether Earth will produce more surprises. It is whether we will learn to recognize the dangerous alignments before they finish forming. The final and perhaps most sobering realization is that no single breakthrough, no revolutionary satellite, supercomputer, or forecasting algorithm will ever fully remove uncertainty from a planet this complex. Earth is not a machine with neatly labeled switches. It is a living system of oceans exchanging heat with atmosphere, molten metal stirring beneath the crust, ice sheets reshaping coastlines, and a restless star constantly bathing the planet in invisible energy. Each layer follows physical laws, but when those layers interact, they generate behavior that is far harder to anticipate than any one of them in isolation. This is why the future of resilience is increasingly being framed not around prediction alone, but around adaptability. Systems designed with flexibility absorb shocks better than systems designed only for efficiency. A power grid that can rapidly separate into smaller, self-sufficient islands can prevent a localized failure from cascading across states. Satellites built with hardened electronics and autonomous safe modes can ride out radiation storms instead of tumbling into silence. Communication networks with multiple pathways can reroute traffic when one link falters. Water systems with surplus storage can buffer droughts and freezes alike. None of these solutions depend on knowing exactly what tomorrow will bring. They depend on accepting that tomorrow will, sooner or later, bring something unexpected. The shift toward adaptability also changes how societies evaluate success. In the past, preparedness was often judged by whether disasters were avoided entirely. Increasingly, it is being measured by how quickly systems recover and how narrowly communities escape worst-case outcomes. A blackout that lasts minutes instead of days. A supply shortage resolved before shelves empty. An evacuation ordered early enough to prevent casualties. These quiet victories rarely dominate news cycles, yet they represent some of the most consequential achievements in modern risk management. Education plays a crucial role in this transformation. Engineers trained today are being exposed to climate variability, cyber-physical security, and space environment hazards in the same curriculum. Meteorologists learn about energy infrastructure. Emergency planners study satellite dependencies. This cross-pollination is slowly producing professionals who instinctively think in networks rather than silos, who expect interactions rather than anomalies, and who design with compound scenarios in mind from the start. Over decades, that mindset may reshape everything from building codes to national security strategies. There is also a growing recognition that communities themselves are part of the system. Public trust, communication habits, and social cohesion can determine whether warnings translate into action or fade into background noise. Clear messaging about uncertainty, what is known, what is not, and what precautions are being taken, helps prevent panic while still encouraging preparedness. When people understand that officials are watching multiple layers of risk at once and adjusting plans accordingly, confidence tends to rise rather than fall. Transparency becomes a form of infrastructure in its own right. The story that began with a single historic freeze thus widens into something much larger. A portrait of a civilization learning, slowly and sometimes painfully, how intertwined its fortunes are with forces far beyond everyday experience. The sun's eruptions, invisible to human eyes, matter because satellites matter. Shifts in upper atmospheric currents matter because forecasting depends on them. Power flows, data streams, fuel deliveries, and hospital operations all ride on physical processes unfolding across scales from thousands of miles to fractions of a second. The fragility does not come from any one of those elements. It comes from how tightly they are bound together. Yet, that same interconnection also offers leverage. When knowledge moves freely between disciplines, when early warnings in one domain trigger preparation in another, when systems are engineered with graceful failure rather than brittle perfection in mind, the outcome of future crises can change dramatically. The goal is not to dominate nature, but to coexist with its volatility, to build societies that expect turbulence and plan for recovery before the turbulence arrives. In that sense, the most important discoveries may not be new physical mechanisms at all, but new ways of thinking about risk. Viewing disasters not as isolated bolts from the blue, but as moments when multiple trends intersect. Treating uncertainty not as a flaw in science, but as information that can guide precaution. Investing in resilience not because catastrophe is inevitable, but because surprise is. And perhaps that is the quiet lesson threaded through every dataset, every simulation, every after-action report examined along the way. The future will almost certainly contain events that defy easy explanation in the moment. Storms that intensify too fast, failures that propagate too widely, disruptions that spill across sectors assumed to be independent. When they occur, debates over causes will follow, as they always do. But the real measure of progress will lie elsewhere, in how few people are harmed, how quickly systems rebound, and how much of daily life continues uninterrupted. Because the ultimate question is not whether the Earth-Sun system will surprise us again. It will. The question is whether the structures we build, technological, institutional, and cultural, will be ready to absorb those surprises without breaking. Long before the next headline appears, long before the first screen flashes red, long before anyone realizes that a familiar forecast has quietly turned into something far more consequential. That is where the story truly ends, not with certainty, but with preparation,